sound. So somebody could please let me know if you can hear me.
We can hear you, Professor.
Okay, thanks for that. Now I just have to. All this technology. So I also have to connect with my iPad. Sorry, it doesn't want to. Okay, so just 1 second. Okay. Okay. Good. Finally, that was a bit. Bit of trouble, but finally we got there. Okay, so let's start. So this is lecture number 13. And the topic today is that we are going to look first then at some example, at least, to cover. So of integrals, where the integrand has branch cuts, so with branch cuts. Okay, so, and given time, perhaps we will go through very quickly these 5 types, but I have decided that we have around 1 hour to look at these integrals, and then I will have to move on because I think the topics that come after are actually more important. I think these integrals you can handle already quite well on your own. So, and of course with the help of the lecture notes that I am writing and that you will have, that will give some more examples that you can work through. So we are going to look at an example of type 5. So again, I haven't given you a classification, but this will be the type 5 according to the Alfors classification here. So I still don't know how many of you or if all of you have access to this book. It would be useful to know. So if you could tell me, that would be good. If nobody has access, it's kind of pointless. So the example, so these are integrals of the form 0 to infinity q of x log to the power k of x dx. So we're looking at real integrals, remember, and we're going to try to use the residue theorem to compute such real integrals. And here k is some positive integer, so 1, 2, 3, and so on. And q is some rational function without, and this is always a key point, so without any real poles. And on top of this, we have some condition on the degrees. So let's assume that this rational function can be written as p over q. Then we want to assume that the degree of sorry, not over Q, that's very stupid. So P over S, let's say. So P over S of X, where the degree of S should be larger than the degree of P, but even larger by, two higher degree than the numerator. And this is for sort of convergence purposes, you will see. So as an example of this, so I think it's more clear to learn by example, and then each of these types, all examples work in essentially the same way. So this is the point of sort of defining them into these 5 categories. So what we will try to do is to compute the following integral. So I will just take k equals 3 here for an example. No, sorry, I will take k equals 2. That's my example. We'll take k equals 2, and q will be x squared, 1 over x squared plus 1. So it satisfies this hypothesis on the degree in particular, right? So I have this integral, and now I want to compute this using residues. So now we will go through this one in detail, and then since this one is a bit more difficult example, let's say, and then I hope that if you can do this, then this will help you enough to be able to cover the easier cases on your own, and of course in the tutorial, which will go through some of the other types. So this is also why I am allowing for the course to not spend several lectures just doing examples here. And also since you have told me that you already have some experience with these things. So let's try to see how we can compute this integral. So what would be the first step? So the integral is here. So the first step is always to choose which complex valued function to integrate. And you also have to choose, of course, the contour. So step one is always to choose the meromorphic function and the contour to which we apply the residue theorem. And now, how should we choose this function? So for the function part, we consider what function? So you know that usually you would do something like, if you wanted to integrate, a polynomial like x cubed over x5 plus 1 or something like that, then you would just take the corresponding complex valued function, you just exchange x for z, right? This is just an example, which I will erase, but it's nothing to do with this thing here. But in the presence of branch cuts, which we will now get, so if we put a logarithm in here, we'll have to make a branch cut, and then we actually have to do something slightly different. So you would think that you would put log squared z over z squared plus 1, which would be just the integrand up here, but I switch x for z. But actually it's not that easy, or at least with the trick that I will show you today, which is how I would usually solve these things. The trick is that you don't put log squared, so you don't just copy and change x for z, but actually you do the following. So let's just erase this and put log cubed of x over x squared, no, sorry, not of x, so log cubed of z over z squared plus 1. And here we really observe this unusual little trick here. that we put the 3. So we put k plus 1 if you have tried to integrate log to the k. Put log to the k plus 1 here. And we will see that this is, why this trick works. So I wanted to show you this integral to make sure that you have seen this, this trick. Okay, and then the next thing we have to do is we have to tell what is the branch cut. So where we choose the branch cut. So how should we choose this branch cut now? Well, usually, so we are interested in knowing about this positive real line, so 0 to plus infinity. And so we have to try to approach this this somehow. And actually the reason for this, so I hope this will become clear as the example goes on. So now I'll just write down what you take. So we choose the branch cut log z. It's defined, so you remember that you always have to define the branch cut, or at least write if you're using the principal branch. So it's equal to the following, where 0 is between, where theta is between 0 and 2 pi. So this is the second thing to observe, that this is not the usual principal branch. So what we have done is, instead of taking away the negative real axis, we have now taken away the positive real axis. And interestingly enough, the positive real axis is where, is the actual line along which we want to know the value of our real integral. And now we are cutting it away. Okay, so the reason for this is that we will choose the following contour. So let me do it maybe in green or something like that. So the contour will be, so it will be a circle going around like this. But when I come close to this branch cut here, I can't just pass. I can't just do this, right? This would be bad. So what I have to do is I have to go around the branch cut, because I have to stay within the domain where my logarithm, where my function is holomorphic, right? So what I have to do is, what you usually do is that you go like this, you go in, and then you follow, yeah, I'm trying to, slightly tricky to draw this picture here. And then you follow a small circle around here, and then you come out on the other side. And this is called Keyhole Contour. Okay, and we will see later what happens. So, well, let's denote these parts. So this is, let's say that this point here is R. So we call this CR, which is the circle of radius R, capital R. Let's call this C of 1 over R. So this would be a small circle of radius 1 over R. And then we have these two line segments here, which we could call, so of course their distance to this branch cut should depend on, it should be 1 over R or 1 over 2R or something like that. So let's just emphasize their dependence by calling them LR and UR for lower and upper. Okay, you can of course decide for yourself which terminology is best. I don't have a standard or preferred choice for this. So you have these 4 parts, and your contour that you consider is CR plus LR plus C1 over R plus UR, where everything is oriented in this direction. Okay, so this is how it goes. So any questions so far? So of course I understand that it's still mysterious why you choose this, this number 3 and perhaps why you choose this branch cut here. So this will be clear in a moment. So first let's, however, compute the residues. So now we have a closed curve and we have this f of z, which is holomorphic everywhere inside. So, okay. So now f of z is, no, not holomorphic, but it's meromorphic. It's defined. And meromorphic inside this gamma of r. Because the inside, of course, is now away from the branch cut, what is called the inside. Okay, and so let's see. Should I explain already now why we have this? No, okay, so let's start. Let's just do the sort of book way, step 1 or step 2. So let's just deal with the residues first. So compute the residues of F. So of course, then we first consider what are the poles of F. So poles of F. So remember it was log cubed z over z squared plus 1. So what would be the poles? Well, so poles are exactly when z squared plus 1 equals 0, because the logarithm doesn't contribute anything away from this branch cut. So we have z is equal to plus minus I. And this means that by the residue theorem, so I always like to recap along the way to know where we are. So by the residue theorem, we have that the integral along this, all of this curve, gamma r, f of z dz, is just 2 pi I times the sum of the residues, residue in I plus the residue of f in minus I, because both I and minus I are inside here, right? So this will be minus I and this will be I. Because R is, of course, large. I'm thinking of this as a large number. Okay, even very large. So R will tend to infinity, of course. So we have this by the residue theorem. So we want to compute the residues, so the things that are in the right-hand side here. And then you just remember, for this, it's easy, so you just remember this formula, first of all. So this is equal to this times F. And F I can write in this way by factoring this, and I can cancel, I, it should be, apologies. So this is z minus I times z plus I. And now these ones cancel out here. Okay, and so this equals to log of I to the cubed divided by 2I. So I just evaluate this in z equals I. But now the question is, what is this? How can I simplify this? Log 2i? Well, that's when you have to be a little bit careful. So you have to remember to always work within the correct branch. So in my branch, or one that we are choosing here, we had that the argument should always be between 0 and 2 pi, which means that everything is fine. And we can say that this is equal to log, but I is equal to e to the I pi half. So we can write it like this, because pi half is between 0 and 2 pi. Okay, and then this is equal to I pi halves to the cubed 2i, which is equal to minus pi cubed over 16. Okay, so we have the first result is that this residue in I is equal to minus pi cubed over 16. Okay, so in the same way, we can compute the residue of F in minus I. So I will still do this because I think this is illustrative. So in the same way, we get that this is equal to just doing the same thing as above, right? But instead of canceling out z minus I, we cancel out the z plus I part. So it will be equal to this, evaluated in z equals minus I, which is now equal to minus 1 over 2i of log of minus I to the cubed. But now again, we remember that we are in this branch. So what is then minus I? Because you might have said that minus I is e to the minus I pi half, but this is not true, because this would not be with within our chosen branch. So we have to just be careful of this trap and write that this is equal to minus 1 over 2i times log, and then minus I will rather be e to the I 3 pi half to the cubed. So just be slightly careful here, okay? To choose the right branch. And then in the same way, this is equal to then minus 1 over 2i times I 3 pi half to the cubed, which is equal to 27 pi cubed over 16. So we have this. And so as a summary, then going back to what we had up here, we then conclude that the integral along gamma r f of z dz is equal to 2 pi I times minus pi cubed over 16 plus 27 pi cubed over 16, which is equal to 13 pi to the fourth over 4 times I. So we get this. Which is purely imaginary, by the way, so this will be important. So this ends the first step, so step 1. And then we have the step 2, or step 3. In my notes is step 2, but whatever. So the next step, anyway, is to estimate or compute each integral involved. So we had these 4 integrals, remember? So we had the keyhole contour, we had the large circle, we had the small circle, and we had the 2 line segments, the upper and lower segment. So this is where it will be explained then why we made this mysterious choice of log cubed. And I reiterate what I said last time, that this is a matter of experience of having seen these tricks, right? So it's not that you would look at this for the first time and just without even trying, just realize it should be log cubed. I mean, you have to play around with it a little bit first. Okay, so we look at the contributions from these upper and lower line segments. So remember, if this was the contour here, like this, then we are now looking at UR and LR being these segments here. Okay, So we're looking at that. So here I just want to emphasize that, you know, I'm not giving a precise parameterization here. I mean, there are several different choices. For example, I mean, at what point here does this lower line meet the circle, and at what point here does the upper line meet the circle? So there are many possible choices here, and you can just do this exercise. Why is our branch not including 0 if we use you mean that we have to take away 0 as well? Yeah, right. Yes. Okay, so let me correct this. Thank you very much for the comment. You're right. Wait, what? What do you mean? No, okay, this was correct. This is just the argument. So who said our branch is not including 0? Okay, so let's read this again and see what is the point. How do we find log of 3 plus 0i, for example? So 3 plus 0 times I seems to be a real number, which is on the branch cut, so we could not find it using this particular branch. But of course, if you wanted to compute this number, you could do it in some other branch. So I'm not sure about the question. So if you want, you can unmute your mic and maybe elaborate on what you mean, or if this answers your question. Yeah, so anyway, so the point is you have to choose a branch which, I mean, avoids this real line and it avoids everything. Okay, good. Okay, thank you. So, but I'm glad you're asking the questions. So this is very good that you are active. So let's see now the contributions. So without going into the specific parameterizations, if we look at this contribution from UR and LR of f of z dz, then in the limit, so I write it like this to avoid, to avoid writing down explicit parameterizations here. So all I'm using is that I think that as r goes to 0, the circle becomes, as r goes to infinity, this circle becomes smaller and smaller, and these lines come closer and closer to the real line. This is all I need, right? And of course, as r goes to infinity, the outer circle becomes larger and larger, so the length of these things goes to infinity, but we come closer to the real line. So I hope it's clear what I mean. So as r goes to plus infinity, I get that these integrals tend to, so the first integral, okay, so let's look at the one from the upper real line. So now we should discuss a little bit here. So the one from the upper real line, it will come closer and closer to, so it will be like this, and then it will grow and it will come closer and closer to the real line. If we imagine this is the real line going off to infinity, then it will get longer and longer and it will come closer and closer. And it comes from above. So here, when you are in this zone here, we have that log z is equal to log r plus I theta. But then as r goes to infinity, this theta part here, this will go to 0 when you come from up here. You'll say that the angle was 0. And log r, well, this will just go to x, to log x. Okay? So let's see, I mean, please ask if you want to discuss this more. So this one, I'm claiming that this will tend to log x cubed. And what I'm saying is basically that log z will be approximately log x in the limit as r goes to infinity when you come from above. Okay, but then something important happens. So you will understand the point of this whole discussion and why we chose this function, hopefully now. So this will be plus, now that we look at the lower line, so first of all, it goes in the opposite direction of this. So the UR, it went in this direction, whereas LR, it went in this direction. So I have to take, so UR, it went from 0 to infinity, but LR, it will go from this point, which is, R, and this is something like 1 over R. So in the limit, this will go up to infinity, but it will go from infinity to 0. So I have to write here then infinity to 0. Or another way of doing all of this is that I put, after all, 0 to infinity, but I change this sign here to minus, because going in one direction from R to 1 over R is the same as integrating minus that function in the other direction along the line. So you remember this, that the integral of minus gamma of f dz is equal to minus the integral of gamma of f dz. So using this, I could put this minus sign here and integrate from 0 to infinity. And here, now the question is, what should I put in here? And the answer now is, so now we should discuss even more from this picture. So now that we come from below here, so if we approach the real axis from below, then our logarithm is something like log r plus I theta, but where theta is close to 2 pi, right? The angle was from 0 to 2 pi. So what we'll get here is log, so, and the log r will tend to log x. So it will go to log x plus 2 pi I cubed over x squared plus 1 dx. And this really is the key secret of why you chose all of this in the beginning. So this is the setup. And the magic now is that if we look now at log cubed x minus log x plus 2 pi I cubed, then this is equal to log cubed x minus these things, and these cancel out, we see already. And this will be the whole point. So we cancel out, and then we get a bunch of stuff that I have to read off my paper here. 6 pi I log squared x plus 12 pi squared I squared log x. So I'm just expanding this parenthesis, right? Plus 8 pi cubed I cubed. And so I can simplify this to minus 6 pi I log x squared. Okay. Yeah, just whatever was there. So I don't have to write it again. Maybe I can try to be fancy. So this is equal to, but I have to put the minus signs here. So minus this plus 12 pi log x, yes, plus 12 pi log x, and then plus 8 pi. Okay, so this is plus and this is plus. If I removed, so I put the plus because I remove this. And I remove this. Okay, so this is what I did. Okay, so it's equal to this. And hence, means, as a consequence now, if we manage to keep track of all of this business, this means that this integral that we had up here, this star thing, so this star, it tends to the following thing, so minus 6 pi I times the integral here of log squared x over x squared plus 1 dx plus 12 pi squared, the integral from log x squared plus 1 dx, and then plus 8 pi cubed I integral from 0 to infinity of dx over x squared plus 1. Okay, and then you see that, yeah, actually, let me write it like this. Sorry. Yeah, so this will imply that this thing, and then plus the remaining things that are on the big circle, plus the integral on the small circle. So when we recap what we had that this was equal to this from what we had up there. If you remember, we computed the residues to know that this was equal to this. And then we will want to equate the real and imaginary parts. So note that this is purely imaginary. So its real part is 0. And here note that this term, for example, is real. All of this 12 pi squared times this is real. So this implies already that this thing has to be 0. And so this integral from 0 to infinity of log x over x squared plus 1, we don't have to deal with this. This integral here, well, it's equal to pi over 2. This is something that you can, you know from calculus, because it's equal to the arctangent of r in the limit, which is pi half, and in the limit, when r goes to infinity of 1 over r, this goes to 0. And pi half minus 0 will be pi half. So this integral will be pi half, so we could deal with all this rest. And then, of course, the big one is this, which is just the integral, which I call I, which was the integral we were interested in from the beginning. So now we know that, so this has to be 0. Well, we don't know that yet, actually. But so we know that this minus 6 pi I times this integral we were interested in here, plus something real, plus, so this one will not play a role, plus 8 pi cubed I times pi half over here. And then these remaining things that we don't yet know what they do are equal to this thing here. So we are almost there. If we could only show that, well, we could only control what happens on the big and the small circle. So remains so actually we will show that the integral along the large circle goes to 0, and the integral along the small circle goes to 0 as well, as r goes to plus infinity. And then we would be done, because if this one, so let's just see what would happen. So this one would go to 0, this one would go to 0, and then we would have just this elementary expression, this equation here involving the integral that we are interested in, and we will be able to solve for this integral. Since we know the value of each of these terms in the limit. So actually, if I want to be correct, I should probably write here the limit. Okay, so we know that this is 0, this limit, and this limit. So equal to 0. Arbitrary limit. So how can we see this? So to deal with the first one, so the large circle. So this is often the hardest part, I would say, is to, I mean, you can learn how to set up all of these things, but then, you know, if it's a difficult integral, then maybe it could be tricky to do these estimates. To show that usually, I mean, it almost always happens in practice in what the exercises that you get, that things tend to zero along these circles. But in order to show it, you still have to give some argument. And okay, what is now this argument that we want to give? So, so the first claim is that this integral here goes to 0. So to prove this, we look at the integral of f of z dz. And we look at the absolute value of this thing along the large circle here, okay? And now we want to estimate this. So we can do the usual thing where we can move. So of course, I mean, now we imagine, by the way, we imagine that it's just a large circle because in the limit, it will tend towards this circle by continuity. So let's just see, and then you can, I mean, you can understand the necessary adaptations here. And when I do this trick, I multiply and I divide by z squared. Okay, so I just multiplied and divided by z squared, and then I moved the absolute values inside, and I remembered to put it on the dz as well, so on the area element. And now, what can we say about these things? So the first thing is that, okay, so what can be said about this term here? So this term is actually bounded. And when we continue our estimates, say that this is less than or equal to this times, when we look at the absolute value of this log term, which is less than or equal to log r, I mean absolute value of log r, but this is log r because r is large, plus 2 pi to the cubed divided by absolute value of z squared, but this is r squared, and then times the integral of this integral times this one, which is equal to 2 pi r. So you get times 2 pi r here. And then this is equal to m log r plus 2 pi cubed over r. And now you have to remember again then some real analysis. Oh, maybe you cannot see the bottom of the screen. Yeah. Okay, so then you have to remember some real analysis to see that this thing here, it actually goes to 0 as r goes to 0 using this thing here then that log r to the k divided by r goes to 0 as r goes to plus infinity, and k is 1, 2. Okay. And then the second point, so this shows that on the large circle it goes to 0. Then what happens on the small circle? So we claim that this goes to 0 as r goes to plus infinity as well. Okay, and by this let me write it in the other way. So now we have a very small circle of radius 1 over r, around 0. And so the proof is that we can write epsilon, which is 1 over r, just for convenience. And we think that we let epsilon go to 0. When this integral along this small circle of f of z dz, this is less than or equal to, again, when the length along the length of the curve along which we integrate, so the circumference of the circle, times simply the maximum value of the integrand on this circle. Oh, is there some more in chat or that you haven't seen? Ah, no, okay, just yes. So you have this, and now we want to see what are these two things. So first of all, this is obviously 2 pi epsilon, and to see the second thing, we do the following estimate. So now, if z, so we have z is equal to this, so it's always of this form on the small circle. So this implies that the absolute value of log z is equal to the absolute value of log epsilon. So this is what log z is, and theta is between 0 and 2 pi. So this one is less than or equal to, or less than, if you want, absolute value of log epsilon plus 2 pi. Because absolute value of 2 pi I is 2 pi. So this was the first thing. The second thing, this is very useful. So it's so useful that I will write it in red. So note that z squared plus 1, the absolute value of z squared plus 1 is larger than or equal to absolute value, 1 minus absolute value of z squared. So this happens, this is used a lot in these integrals. So what is the proof of this? Well, it's elementary. It's just the triangle inequality, but in a maybe unusual form. So I'm sure you've seen this before, but it's just that the absolute value of 1, you can write it as the absolute value of 1 plus z squared minus z squared, which is less than or equal to the absolute value of 1 plus z squared, plus the absolute value of minus z squared, but that's just the absolute value of z squared. So this, moving this to the other side, it says that absolute value of 1 plus z squared is larger than or equal to 1 minus absolute value of z squared. So this proves that. The thing in red. And so using both these things, and noting that this is then equal to 1 minus epsilon squared, because epsilon was the absolute value of z squared, and this goes to 1, as epsilon goes to 0. Then we see finally the following. So we wanted to look at this thing up here. So we wanted to see that finally 2 pi epsilon times the absolute value of log epsilon plus 2 pi to the cube over 1 minus epsilon squared. So this goes to 0 as epsilon goes to 0. And we'll try to justify this by saying that epsilon log k to the epsilon goes to 0 as epsilon goes to 0. And then this thing here just goes to 1. So, okay, so along such lines, you try to show that try to show that this large and small circle goes to 0. And then let's see, where was my last page? Otherwise, we'll have to just do it by hand. Okay, well, I had it somewhere. But it seems to have been lost. It's here. Okay, so putting it all together now, so we have that, you remember we computed the full integral was equal to this, and then we had, so this being the integral that we are interested in. So we had this plus 12 pi squared. So let me still write this one, even though I remarked that it had to be 0 because of this abstract argument. Plus 8 pi cubed I integral from 0 to infinity of dx over x squared plus 1. Okay, so we had this and then plus 0, which was the contributions from the large circle in the limit, and this was the limit of the integral along the small circle. And as I said, I already remarked that this was equal to pi half, and this has to be 0 because it is real. And we knew that this total thing was equal to something purely imaginary. So equating real and imaginary parts, we get that 13, so the imaginary part of 13 pi to the 4 over 4 times I is just what is left when I take away the I, of course. So minus 6 pi times the integral that we were interested in, plus 4 pi to the 4. And this means that we can solve for I, and we get that this I is equal to pi cubed over 4. And this is finally, after all these pages, the solution to our problem. I mean, we computed the integral. And along the way, and as a byproduct, by doing all of this, we also got this other integral for free. Without any extra work. But it was already a lot of work, so. But it's anyway nice to note how this works, this equating real and imaginary parts to get these things. So, any questions for this one? I understand it was long. You will have it in your notes, all of this, so you can read it. Okay, so let me just then maybe give you a very quick recap of these 5 types. So quick overview of the 5 types. So the purpose here is just that so you have seen, so I make sure that you have seen what these types are, so that you know, in case you feel that, oh, I don't know how to solve this kind, you can look at it more closely. So the first one, according to Alfors, is trigonometric integrals. So of this form, r of cosine theta, sine theta, d theta, where r of xy is the rational function with no poles for x and y on the unit circle in R2. Okay, so example could be, something like integral of 0 to 2 pi of typically 1 minus 2 cosine theta, well, 2a, so maybe 4. So it's a typical integral like this, actually, where you compute this. This is a good exercise for you. I put this one in the notes, where a is some complex number with absolute value less than 1, for example. So you can try to compute this and see that this IA is equal to 2 pi over 1 minus I squared. So you can try to check this. And the trick to do this kind of integral is to substitute, to make a substitution. Z is e to the I theta, such that cosine theta is 1/2 Z plus 1 over Z, and sine theta is equal to 1 over 2i, Z minus 1 over Z. Okay, and when you make this change of variables, taking into account that dz is then equal to I e to the I theta, if you just brush up on your change of variables from calculus, you will get this. And this will lead to computing this I. This was I up here. So I would be equal to, then integrating, so we integrated from theta from 0 to 2 pi, so this is the same as integrating along the unit circle now, of this r of z plus 1 over z over 2, z minus 1 over z over 2i, dz over iz, and so here there is nothing with, nothing else going on when integrating along this circle here, and computing the poles and so on. So this would be equal to, by the residue theorem, this would be equal to 2 pi I sum over j of the residue, sum of residues. Okay, but actually I don't want to write all of this, so then just apply residue theorem, because I want to very soon pass on to the next topic. So this was the number 1. The number 2 is just the integral from minus infinity. So this is probably the simplest, nicest looking one, where q of x is a rational function. But it's important to remember that it should have no real poles. And we also ask that the, if q of x is equal to p of x over s of x. So just like earlier, we ask that the degree of s is greater than or equal to degree of p plus 2 to assure convergence. And this one is calculated along such semicircle contours, and just integrating the q of z, so you just change x for z, dz along this gap. So you just do the same thing. So this is the easiest one, and apply the residue theorem. Then you have a similar type, so which type 3, which is this I, which is minus infinity to infinity of q of x e to the I alpha x dx, where alpha is some real number, and alpha is not 0. If it is, we see case 2. Q of x is rational with no real poles, and the degree of, so it's equal to p over s, degree of s is greater than or equal to degree of p plus 2, but actually also 1 is possible, but this is a bit more tricky. You can look in Alfors for this. Okay, and the example, so we already saw an example. This minus infinity to infinity of e to the I x over x squared plus 1, which also gave the integral of sine x over x squared plus 1, and it gave the integral cosine x over x squared plus 1 as the real and imaginary parts. And this one was also, you used the Jordan lemma and this kind of contour. On the other hand, there are exceptions that if you have sine x over x, for example, with a removable singularity at z equals 0, you tend to anyway avoid this one. So you go around, this is 0 here. So you go around 0, and so you have this CR, C1 over R, and then the rest. So these line segments here. Okay, so you can be aware of this, this exception. The number 4 would be, so now we have branch cuts. So this is considerably more complicated. So you have one of these to figure out for, so we saw one now for the logarithm just now. And you have another one to figure out for your homework. Okay, so this one, so it's like a square root, right? So for example, the integral of x to the 1 over, I always put x squared plus 1, but of course you can have other things. So alpha is between 0 and 1, q of x is equal to p of x over s of x. Rational, the same hypothesis with degree s greater than degree of p plus 2. And an extra thing, and no poles on 0 to infinity. So this is important because you want to choose the branch cut sometimes, at least with this logarithm, so that it's on this part. Okay, and then number 5 is what we saw. So it was the integral this integral from 0 to infinity of q of x log to the k of x dx, okay, 1 to 3, so on. And q of x was rational. So equal to p of x over s of x with no real poles, and degree of s is greater than or equal to degree of p plus 2. Okay, so just to show that there is such a classification, and now you just have to practice. Okay, so do the homeworks read Alfors to get some more hints about which contours to use. So this one, of course, uses usually the Keyhole Contour. Okay. And try to just make sure that you master these 5 types. And once you do that, you can often reduce other integrals to these types. Okay. If you want to insist on doing more advanced things using the residue theorem, which in this course, I mean, I won't really insist on that, so it won't get much more difficult than the example that you just saw, which is already a long computation. Okay, so any questions about that? Or otherwise I will skip to the next part. Now I see someone wrote something in the chat earlier. So you can unmute and use your mic if you want to get my attention, because I didn't see this one. Yes, so Emil Mukhin, so which integral were you talking about at that point? So it was 5 minutes ago. The integral at the beginning. No, I'm not sure which one you were talking about, but yes. So anyway, there are definitely some substitutions and things that can make these things easier, and even avoid the branch point sometimes. Yes, absolutely. So again, so if you have access to Alfors, you should go and read this because we have some alternative clever ways of solving these sometimes. Okay, so if you have some additional comments about that, feel free to write or use your mic. And otherwise, if there are no further questions, let me go to this next part, which is on the local behavior of analytic functions. And the goal is to prove the so-called open mapping theorem and the maximum principle and so on. So it will go along these ways. So today we will just look at this open mapping theorem. So what we are doing is we are looking at more special properties of analytic functions to try and understand them. So we start by an example. So consider this z goes to z squared. Then we can draw a picture, something like this, perhaps. So if I restrict to half of the disk, so this one will map half of the disk to what? So it will map half the disk to
full disk without
the disk, right? By z goes to z squared. And so even more generally, I mean, if you map the whole disk, then you can view it as going around twice and so on. So the point here is that for W non-zero, so this is the W plane, and this is the Z plane. So for W not zero, there are exactly two pre-images. So what I mean by that is that Z squared equals W has exactly two roots. Okay, and this is moreover true. So true also for W equals 0 actually. If we do what we did last time, so if we count multiplicity, since so Z equals 0 is a double root. okay, of the equation z squared equals 0. So the point here, so let me underline, so we have exactly two preimages for z goes to z squared. So now, more generally, we can of course also consider the exact analogy for z goes to zn. So then we have, if we take z is of a form r to the e I theta, where r is, so we look again at this circle, right? So unit circle. So r is, this is an open interval. So 0, 1, and theta is in 0 to 2 pi. Then this, under this map, z goes to zn, we see that r e to the I theta is mapped onto r to the n e to the I n theta. Okay, and Rn, this one will still be in 0, 1, of course, but this one will wind around, so this one will wind n times, so to speak, this one will possibly wind around 0, so let me just say that we get some winding here. So one way of viewing this is that the image that you get is the same circle, so but covered. So this is this circle and this is this circle, but you get it n times in a suitable sense. Okay. So what do I mean by this? So what I mean is that f of this disk, so you can also call this d. It's easier to write. So f of d covers d n times. Saying this means, so by this we mean that the equation w equals z to the n, so w is here, so has exactly n solutions. So up to multiplicity. Again, okay? And so in general, so now the question is that if we look at the even, so in the general case, so for any f of z holomorphic with a 0 of some order n at the point z0, then actually we can decompose it in a way that makes it look quite similar to this z goes to zn. And it's this decomposition that we have seen countless times. So it's equal to this, g of z, where g of z is holomorphic on the neighborhood of z0, and g of z0 is non-zero. Okay, so this one looks, locally, it looks similar to z goes to zn, thinking that, okay, this is something holomorphic, so this one will stay bounded close to z0, whereas this part here, z minus z0 to the n, this one will become very, this will be sort of a dominating behavior here in a suitable sense. So the question, so all of this will be made precise here. So the question is, if f of z equal w has n solutions, so for example, as was the case for f of z equals z to the n here, then is the same true for f of z equals a if a is close to W. Okay, so this is the question. So is this property of having n pre-images preserved in a small neighborhood of this point? So this may sound like a sort of silly question, a strange question, but the remark is that if you think about real analysis, I mean, it's presented like this, it sounds obvious, like, okay, why shouldn't this be true? But if you think about what it actually means, so in real analysis, this is completely false. So if you look at x goes to x squared, so it looks something like this. Then you see that x squared equals 0 has two solutions after multiplicity, of course, whereas x squared equals, minus epsilon, for positive epsilon, has no solutions. So it means that even though epsilon is really approximately 0 here, and when you look at the equation x squared equals 0, it has exactly two solutions, then the equation x squared minus epsilon loses all of its property. So for real analysis, this is not an open property, so to speak, too. But locally, it is preserved the number of zeros of an equation. But the claim is that in complex analysis, so in complex analysis, the number of solutions to an equation, so a holomorphic equation, an equation involving holomorphic function, so f of z equals a, is for f holomorphic, is preserved locally. And thanks to this example, we now understand that even though, for very nice functions like this real valued function, this thing fails completely. So it's another very special property thanks to this holomorphic condition. Okay, and so to make this rigorous, we have the following proposition. It says that suppose that f is holomorphic at z0, f of z0 is equal to w0 with multiplicity n, so meaning that f of z minus w0 has a 0 of order n, z equals z0. Then we have the following. So then for every, and this is a very important part of this statement, so for every sufficiently small epsilon, so this I have to underline, for every sufficiently small epsilon, there exists a delta such that if A is in some small disk, so we have these two disks, right? So we have, maybe make it a bit larger. So we have Z0, and we have this radius to be epsilon, and then we have another disk around W0 with radius to be delta. So if A is inside here, okay, so if A is there, then f of z minus a, or if you want this equation, f of z equals a. So, but this function here has exactly n zeros up to multiplicity. In this disk around z0 of radius epsilon. So up to multiplicity, this A here has n pre-images in here. Okay, and this means then that, okay, so also this equation f of z equals a must have n solutions. If a is sufficiently close to W0, where the equation f of z equals W0 had n solutions. So this is what this proposition says. Okay, and this is, again, then in total contrast to real variables. And you'll see that in the proof, we use the argument principle, or we use winding numbers. And all of this is, of course, very special for the setting with holomorphic functions.
Professor?
So the proof is that, first of all, since zeros, so now we're going to use this sufficiently small hypothesis here. So since zeros of f are isolated, we may, without loss of generality, take z0, well, assume that z0 is the only root of f of z minus w0 in this disk of z0 epsilon. So this is what is meant by sufficiently small. So of course, if the roots of this w0, if they were here and here and here, then you take it to be a smaller disk, and you can always take such a small disk around z0 such that such that it only contains one of these zeros. Okay. And so this was just a little technical setup. And now we consider, so what we want to count is the number of zeros, right, of this function. So we introduce, so the main step is this. So z of a is defined like 1 over 2 pi I, where we integrate along this circle of radius epsilon of f prime of z over f of z minus a dz. And now what does this quantity here represent? So any ideas? What this represents? Okay, so this one, if you remember from earlier lectures, so this will actually be, and this is the key observation, so number of zeros of the function, okay, so let's give it a name. So g of z, which is f of z minus a, in this disk z0 radius epsilon. And this is by the argument principle. Okay, and now we want to show, that z of a, so the number of zeros in this disk of radius epsilon of this equation, let's put GA here, right? So this equation, or the zeros of this function, is equal to the number of zeros of the corresponding function, but where we put W0 here instead. Okay, so this is what we want to show. And how do we do this? So to do this, note that z of a, so using the notation that I wrote up here now with GA, so this is equal to 1 over 2 pi I, so over gamma epsilon, so gamma epsilon is this epsilon e to the it, where t goes from 0 to pi. So this circle. So the integral here of GA prime of z over GA of z. So this is just having changed the names with this integral and noting that the subtracting by a constant doesn't change the derivative, of course. So this is equal to this. This is equal to 1 over 2 pi I times, okay, some other curve, which I will call sigma epsilon A of dw over dw. So this is what we did when we were looking, some lectures ago, when we were talking about the argument principle. So this sigma epsilon A is a so-called image curve. So it's GA composed with gamma epsilon, so image curve. So remember this from a few lectures ago. And then we can also look at another image curve, so gamma epsilon, which is just F composed with gamma epsilon. Okay, so of course you have this, this circle here, but then this one might be sent, so it's gamma epsilon, that this one might be sent to something much more complicated, right? It might be sent to something like this, for example. This could be the image curve, an example. Okay, so why do I draw this? Well, the point is that now if we call this star, then this star thing here is just the winding number of this curve sigma epsilon A around 0. So it's the number of times that the function f of z minus a winds around 0, but this is the same as the number of times that the function f of z winds around a. So it's equal to this winding number here. Okay, so because of this, so winding around 0 corresponds to, so G is F minus A, so corresponds to F composed with gamma winding around A. Okay, but now we remember that winding numbers are constant on connected components defined by this curve here, gamma epsilon. So this means that n of this gamma epsilon A is equal to n of gamma epsilon in W0 if we are in the same connected component. Okay, defined by this gamma epsilon. But we can always arrange that this is the case then, because if W0, so the end of a proof is just this, but if W0 is here, then we can take a small disk such that this one is inside some connected components, and then for any of these A inside here, all of this argument will hold. So to finish this, we just say that, okay, since W0 is not on the image of gamma epsilon, there has to be such a circle, and the reason for this is that f of z0. So there has to exist such a disk of radius delta around W0, which does not intersect with the curve, meaning it is in, so see picture, meaning it's in the connected component defined here by it. And this means that for any A in this disk, Z of A is equal to the winding number of gamma epsilon of A is equal to, by constancy of the winding numbers, W0, which is equal to the number of zeros of this equation, Z of W0. So this means that this means that since f of z equals W0 has exactly n roots inside gamma epsilon, the value A is also taken, let's put it this way, it's also taken n times. So f of z equals A also has n solutions in gamma epsilon. And now we have then proven this, this remarkable theorem. And that's an important corollary. Let me just state this, and then we finish. We get the open mapping theorem, which says that a non-constant analytic function maps open sets onto open sets, which is again then a very special property. And the proof is just to interpret the above proposition. Okay, and so you can think about this. It's really just one line, just understanding why, if you open, this will imply that f of u, provided that f is holomorphic, this should be open. This is what the theorem says. And again, this is in complete contrast with this example, x goes to x squared, which sends, same example, this one, which is open, is sent to 0, 1, which is not open. Okay, so contrast to real variables. Okay, so let me end there. Next time, I guess I will just tell you in 1 minute what is the proof, how you interpret the proposition to get this, but it's not at all a big thing. And then we will continue working more on these local properties, going towards the maximum principle, and then we look at automorphisms on the disk, Schwarz lemma, all of this kind of things. So this will hopefully be a nice lecture. But for today, it's over. So let's go for lunch. And of course, this is the moment when I ask if you have some questions.